So the experiment we are doing here is titrations, yes. So obviously we had a whole chapter pretty much talking about titrations. Um, so a reminder, obviously when we do a titration, we use a burette, usually, very badly drawn burette. We will have a beaker. And in this one, we're going to basically be doing acid-base titrations. And in most of our titrations here, we will be having the acid on the beaker. We'll have our base up on top. We also want to always include an indicator. So we talked about indicators as well. Remember, an indicator is really something that will change color and really allow you to know when you should stop your titration. When we do a titration, and titrations that perhaps you've done before, we typically want to stop at what's known as the equivalence point. And the equivalence point in sort of a acid-base titration, as we've talked about, is the point where the moles of the acid will equal the moles of the base. So that's really the point exactly where you've hit that. You've hit the point where you've added exactly enough moles of acid to neutralize all the moles of your base. The overall reaction that is sort of happening in these guys, right, is an acid plus a base, and it typically will react to make a salt plus some water here. And really at that point, when you hit the equivalence point, you pretty much have used up all this guy, you use up all this guy, and you have pretty much these guys left over at the equivalence point. And when we choose an indicator, indicators work over a pH range that we talked about. So for example, that phenolphthalein works, from like 8.3 to 10-ish. And around 8.3, it's sort of colorless, and then it gradually gets that pink color as you head towards the 10 sort of pH there. And in a certain type of titration, this is a really good indicator, especially one where, the equivalence point is somewhere around there in terms of the pH. So you can visually see the indicator change, and, you should stop your titration. Where we typically stop the titration is known as the endpoint. And in a good titration, your endpoint of your titration should be pretty close to your equivalence point. When we do these type of titrations, right, or we do calculations that involve titrations, this is where we talked about we should do it in moles, right? Because we're constantly adding volume, which means the molarity is constantly changing, but the moles are pretty much remaining the same. And remember that when we sort of start a titration, you really only have so many moles of your acid, for example, in there. And that's really what's reacting as you start adding your base. And that's really the moles of your base you're adding. And it's really those two things that are coming together and reacting. And at some point, you will hit that equivalence point where these guys essentially will be used up. Now, when we look at a titration, and as we talked about in class as well, we oftentimes can plot a titration curve. And a titration curve, right, is pretty much the badly drawn one here, but pH versus a volume of base added. Let's see if I can straighten that line out a little bit. And in a sort of acid-base titration, if you have your acid in your beaker to begin with, we typically see in terms of a titration curve this sort of S shape that sort of occurs where we have our equivalence point sort of in this area here. And again, we're sort of cruising and then kind of coming up to our equivalence point there. And that's going to erase the whole thing, isn't it? Let's see. I figured. So there we go, a little bit better maybe. And we talked about a couple of things, especially as we approach the equivalence point, right? And we talked about the idea that it does go pretty vertical as you go this way. And that's what we talked about, that, when you do use your indicator, you oftentimes can see a pretty big jump in the color of the indicator. So if you've used phenolphthalein before, again, maybe you've only added a drop or maybe 2 drops, and it goes from almost like no color to like super dark pink. And that's because as we approach the equivalence point, typically in titrations, we are going pretty vertical. And when we go vertical, as we talked about, what that means is the volume is really not changing, but the pH here is changing a lot. And by even just adding a drop or 2, as you get near the equivalence point, you can see a pretty big change in the indicator. And that's because, you really jump pH units. So maybe you did get up to around the 9-ish range or 10-ish range in terms of pH. And we would make your phenolphthalein, for example, go from kind of colorless to like a light pink or dark pink sort of color. And as we talked about, if you really only missed it by a drop or 2, in the grand scheme of things, you'd probably be okay, because even if you were up here, for example, by only adding a drop or 2, in terms of volume, you're probably fairly close to where the equivalence point would be. You're only in trouble if you kind of open it up a lot, as we talked about, and you really overshoot it, right? And you end up over here. Obviously, that's a big difference in terms of the volumes in each of those things. So, if you're kind of going drop by drop as you're sort of doing your titration, and you're going really slow and you're kind of adding drop by drop, even if you sort of visually miss it with your indicator and it turned really dark, if you're really going that really slow, you may still be in the right volume in terms of the equivalence point, again, because of that verticalness that's happening as you're adding. So in this particular experiment, we are going to be looking at a couple of things here. In part 2 and part 3 of this experiment, your goal is to sort of make these titration curves. So to make a completed titration curve is sort of your goal. And you're going to use that curve to figure out certain things. You're going to use that curve to figure out things like the Ka value, pKa value, try to identify maybe the molar mass of your weak acid, what the identity of your acid may be as well. So we're going to kind of use a lot of these things to help us figure out some properties of these acids. But in part 1, let's start with part 1 and sort of what's going on in part 1. In part 1 of the experiment, we're actually going to standardize our sodium hydroxide solution. So in person, and a lot of times when you do these experiments, and even probably in Chem 50, if you physically did the titration experiment, part of the process is you typically will want to sort of standardize your sodium hydroxide solution. So what does that mean? What that means is you're going to do a bunch of titrations to really figure out what the actual molarity is. And this is usually done because in a lot of cases, we perhaps make the sodium hydroxide solution. And sometimes we don't really want to make it, we kind of want to make it fast, if you will. Maybe we don't want to be super careful as to how we're going to make the sodium hydroxide solution. Maybe we just want to dilute it with about, say, 600 milliliters of water. We don't really want to measure out the 600 milliliters of water and kind of do it as accurately as we can. And what we could do is we could do a set of titrations and using stoichiometry to basically figure out what the molarity of our sodium hydroxide solution is. So in part 1, that's sort of what's going to happen here. You're going to take your sodium hydroxide solution. You're going to do some titrations with KHP. KHP is a monoprotic acid, and that is potassium hydrogen phenolate is really what that is. That's what the KHP stands for, potassium hydrogen phenolate. By the way, KHP is just the abbreviation for it. It is not the actual chemical formula, which a lot of people for some reason think it is. The actual chemical formula for KHP is something like this. So that's the actual sort of chemical formula that's happening there. And when we react this with our sodium hydroxide, we are going to get a reaction of H2O plus our C8H4O4 and 2 minus in this particular case. By the way, there's a couple of sodiums and potassiums floating around, not really important. You could even get rid of them here if you want and just look at the reaction like this. And this is basically what's going to happen here. So we have an acid-base reaction. We're going to do this titration, and we're going to do it because we know how much of, say, the KHP we're starting with. So we could do a titration where we basically measure out a certain amount of KHP. We dissolve it in some water, and we're able to do our titration. So we would titrate to the endpoint, and we can figure out, you know, the concentration of our sodium hydroxide. And we could do that by, excuse me. Just give me one sec here. By doing our titration, like I said, to the equivalence point, and we could do some stoichiometry. So what do we know in this case? So in this case, again, our sodium hydroxide will be up in our burette. Our KHP will be down here. Obviously, we'll put some indicator in there as well. And as you do the titrations, you will titrate to the equivalence point. So you're going to titrate to the equivalence point. And what we're going to do is you're going to be able to figure out the moles of KHP from your titration information based on how much you start with. You will then be able to go mole to mole relationship between the KHP and the NaOH. So in this case, because it's a 1-to-1 relationship, there is 1 mole of KHP gives you 1 mole of sodium hydroxide. So really the moles of KHP here will equal the moles of sodium hydroxide. And once you have the moles of sodium hydroxide, you can use the volume of sodium hydroxide to reach the equivalence point that you added. And that will get you to your molarity. So you're basically going to do a titration with sodium hydroxide and KHP. You're going to titrate it to the equivalence point. Using the information for KHP, you'll be able to get the moles of the KHP. And again, because it's a 1-to-1 relationship between the KHP and the sodium hydroxide, that will give you the moles of sodium hydroxide. And then you will divide that by the volume of sodium hydroxide required to get to the equivalence point, obviously in liters. And that will give you your concentration of sodium hydroxide. You will do that a few times, I believe. So you'll do it, I think, maybe 3 trials worth. So you're going to do this titration 3 times. You then can get an average value for the concentration of sodium hydroxide after you do that. Any questions on part 1? You're obviously going to be doing this using the Chem collective software like we use for the hydrolysis experiment, also the buffer experiment. So you're going to use kind of the same software where, again, you can actually do the titration, and you'll need to record, obviously, things when we do titrations. We want to make sure that we record the initial burette reading. We want to record the final burette reading when we're at the end point or equivalence point, hopefully, of your titration. A reminder, right, when we look at a burette, typically 0's up on top, and then it increases as you go down. So if you find yourself somewhere here, this is actually going to be 2 point something, right? Milliliters, not 3. So again, it increases as you go down. So you want to make sure that you record the proper volume reading. Obviously, to find the volume of NaOH added, that is your final volume minus your initial volume, right? That will give you the actual volume that you added. So that is essentially part one there. You're basically going to, with this software, do the 3 titrations, and you're basically going to be able to come up with what the actual sodium hydroxide concentration is and standardize it. Any questions on part 1 of the experiment? So not too bad, part 1. So part 2 of the experiment, we're actually going to be doing 2 different titrations. And in part 2 of the experiment, really the goal of part 2 of the experiment is to basically get some titration curves. So we're looking to actually make some titration curves. And in part 2 of the experiment, we're going to be doing 2 different types of titrations. We're going to be doing an HCl and sodium hydroxide titration. We will also be doing an acetic acid and sodium hydroxide titration. So we're going to be doing both of these titrations. And what we're going to be doing is trying to really titrate it until we get sort of the complete curve. So we should recognize both of these types of titrations. This is obviously a strong acid and a strong base titration, while this one here is a weak acid and strong base titration. So we're going to basically kind of set these up the same way. Again, you're going to use that simulation software, and you're going to do both of these titrations. You'll have to obviously grab the flask, the indicator, you know, all that other stuff there, are the burette and all that stuff off the workbench, and set it up like you kind of did before with some of the other experiments. You're going to do some titrations. You're going to add sodium hydroxide into your beaker until you get about a 0.2 pH increase, and you're going to kind of really slowly add the sodium hydroxide and get the corresponding pH. So what you're trying to really do, for example, in the HCl and sodium hydroxide titration, is just that. You're going to slowly add your sodium hydroxide, and every so often you're going to take a volume reading and also obviously a pH reading, and your goal is to get a bunch of points, really, you know, to sort of build your titration curve. And we're actually going to go past the equivalence point in these titrations. So what we're looking for is sort of the whole kind of completed titration curve all the way up. And I think it's somewhere around a pH of 12, maybe. I think, you know, it tells you can kind of stop. So you want to kind of slowly add this just like you would in person. You want to be careful as you're adding it. You want to then make sure along the way that you're recording volumes and pHs. That way, obviously, you can reconstruct this curve. You could do some analysis of it. So I think there's some notebook pages where you can record, you know, the volume and the pH. And again, you want to follow the instructions. Again, it tells you to add it sort of slowly. You're looking for a very sort of a small pH change of about 0.2 pH units. And then you can add a little bit more. Remember that as we do reach the equivalence point, typically what we see is, you know, a lot of times you do see sort of a jump in pH to the equivalence point. And then usually we kind of see a jump after the equivalence point. So, you know, as you start to see the pH change, and typically when you're doing this, you start to see a little bit bigger of a change in pH, a little bit bigger of a change in pH with less sodium hydroxide being added. And at some point, when you try to move in this direction, you want to kind of go as slow as you can and not add as a lot. The important part of these titration curves is really, you know, in this area here and also in this area here. So for the analysis part of titration curves, those two areas are really the important parts to have a good amount of points and stuff like that to allow you really to do some good analysis. So the goal here is to sort of build the entire titration curve using the software. And since this is a strong acid and strong base, we really should know that the equivalence point here, if this was it, should be around a pH of 7, right? Because when we do this titration, we are left with only a salt and water at the equivalence point. That salt is a neutral salt, so the equivalence point here, right, should be in that pH of 7 range, give or take. Any questions on that titration there? The other titration that you're doing is obviously the acetic acid and sodium hydroxide titration. And same setup as everything again. Sodium hydroxide up in the burette, your acetic acid down there in the beaker or flask or whatever you're using. And it's really the sort of the same goal here. We're going to try to go slow. You're going to add sort of the same way. And again, here your goal is to build that titration curve. Again, you should kind of see a kind of a big jump to the equivalence point and another jump past the equivalence point. And again, the goal is to hit it to like maybe a pH of 12. And again, get that entire curve that's happening. But because this is a weak acid and strong base, what we know about that is the equivalence point should be basic. And again, it should be basic here because when you reach the equivalence point, you are left with a salt. And that salt came from a weak acid, which means it will act as a base, the salt, and it will accept an H+, and it would ultimately produce hydroxide here at the equivalence point. And that's why we know it should be more basic when we do this titration. Any questions on that there? So again, you're looking for a good titration curve for both of those. And what is the titration curve going to help us kind of achieve? Well, it will help us achieve a couple of things. It will help us achieve some information about our acids, and especially for our acetic acid and our sodium hydroxide titration, it will help us figure out things like pKa or Ka values, in addition to other things, but it will help us kind of figure that stuff out. So let's see how that will, what's sort of important when we look at a titration. So especially for this type of titration that we're looking at here with our acetic acid and our sodium hydroxide, when we look at the titration curve, and we'll call the equivalence point somewhere here. There's really kind of two locations on the curve here that's kind of important. The first is the volume at the equivalence point, and I apologize for the bad straight line, but we'll just call that straight on down. And we'll say this is the volume at the equivalence point. And for the sake of argument, we're going to say that that is 10 milliliters, for example. Now, the other sort of important point is once you figure out the volume at the equivalence point, is half the volume to the equivalence point. And in my particular example here, the volume to reach the equivalence point was 10 milliliters. Half of that volume is 5 milliliters. So what you would want to do is go back to 5 milliliters. And you would want to go up if you're doing this old school. And then you would want to go over very badly. You want to go over straight. We'll go that way. And when you go over, at that point, at half the volume to the equivalence point, the pH will equal the pKa value for that acid. So at half the volume to the equivalence point, the pH at that point should equal your pKa value for your weak acid. So you may say to yourself, how is that? Or why is that? So let's take a look a little bit closely at, say, an ice table. And let's take a look at an ice table for what we're dealing with, which is basically acetic acid plus some sodium hydroxide, going to give us some sodium acetate plus some water. And let's say that we were first at the equivalence point here. So let's see what happens at the equivalence point. Well, if we were at the equivalence point and I did my ice table, which I would do in moles, and if I started with 4 moles of my acetic acid, since I am adding the sodium hydroxide and we're at the equivalence point, I should have 4 moles of my sodium hydroxide. That means that the change would be 4 moles, 4 moles, plus 4 moles, which means at equilibrium, we would have none of those guys, and 4 moles of this guy. So at the equivalence point, we have this salt, right? We could convert to molarity by dividing by the total volume. And it is this salt, which is the acetate part that's going to react with water. It's going to accept an H+, right? And when it accepts an H+, it will make acetic acid plus some hydroxide. And this is why, again, at the equivalence point, we would expect our pH to be basic. So what happens if we're not at the equivalence point, but we are at half the volume to the equivalence point? So if we're at half the volume to the equivalence point, and if we look at our ice table, and we do our same sort of calculation. So again, I'm going to say I started with 4 moles of acetic acid. And to reach the equivalence point, I need to add 4 moles of sodium hydroxide, which means if I only got halfway there, I would not have added 4 moles of sodium hydroxide. I would have added half of that, which would be 2 moles of sodium hydroxide. That means that I have not reached the equivalence point yet. And that means that the sodium hydroxide is going to be used up. And that means when I reach the equivalence point after adding only 2 moles of sodium hydroxide, I will have 2 moles of this guy, none of this guy, and 2 moles of this guy left. And if I look at my ice table, and this is something you probably already know, but let's just make sure. When we look at our ice table, what I would have left at this point is acetic acid and sodium acetate. So these are really the 2 things that I would have left over at this point in the titration. And those 2 things are related to each other. And as we would expect, and as we talked about, before you reach the equivalence point in a titration of a weak acid and strong base, you will always end up with a buffer. So if you remember, we end up with a buffer here. And because we end up with a buffer, we could use the Henderson-Hasselbalch equation, which is the pH is equal to the pKa plus the log of the base over the acid. That means in this particular case, we would have the pKa plus the log of 2 over 2 if we put our numbers in, which gives us the log of 1, which means that this is equal to 0. And that is how we know that at half the volume of the equivalence point in a titration of a weak acid and strong base, the pH at that point should equal the pKa value. Again, because we should have a buffer going on, we should have equal amounts of the buffer, both the weak acid and the conjugate base, which means that it will basically cancel out and we will be left with a situation where we are exactly at the point where the pH should equal the pKa value. Question on that? So why is that important? Well, that's important because now that we know the pKa value, remember to calculate the pKa value, that is minus the log of the Ka value, which means if I wanted to calculate the Ka value, that would be 10 to the minus pKa. So if you have the pKa value, you then can use it to calculate the Ka value of your weak acid in that particular case. So that's one of the things that you will have to do here in part 2 and also part 3 of this experiment, is to use your titration curve and figure out what the volume is to reach the equivalence point. You then need to figure out what the volume is at half the equivalence point. And you can also figure out the pH at that point. And that will allow you to figure out, that'll allow you to figure out the pKa value and also the Ka value from that. In addition, you'll need to also figure out the concentration, perhaps, the molarity of your acid. And again, that's going to involve stoichiometry, again, from your volume of sodium hydroxide used and the molarity of the sodium hydroxide. You could get the moles of sodium hydroxide, which then from the balance equation, you could go from moles of sodium hydroxide to moles of your acid, which will then give you moles of your acid. And you could divide that by the volume of your acid that you used. And that will give you the molarity of your acid. So a basic sort of stoichiometry problem where you can use stoichiometry and volume to kind of calculate your molarity of your acid as well. Any questions on those calculations there? So how are you going to be able to really sort of hone in on sort of where your equivalence point is, where the volume of your equivalence point is? You can actually do it a couple of different ways. The easiest way is to have sort of a computer program do it for you. You could do it yourself if you know how to punch it all into Excel. I would probably recommend using sort of the computer program to do this for you. And what it's going to do is really make a first derivative graph. So basically what you're going to be able to do with sort of this software is you will have your regular sort of titration curve that you made. And then through calculating really what is known as the first derivative, And it's really just kind of taking some differences between all the points in the volume. You'll be able to overlay another graph where you'll kind of see a peak. And I apologize for drawing it really badly here, but I'll do my best. Much prettier picture in the actual experiment. It'll kind of make a peak like so. And where you see this peak on your derivative graph, that's going to be usually your volume at the equivalence point. So you could use that to figure out the volume at your equivalence point. And I think through the software, it will let you kind of work your way backwards and again, be able to figure out, the pH at half the volume of the equivalence point. So you could use this sort of graphical software to help you sort of analyze it. The data analysis is written for you to use it with the instructions on how to use it. And it's from Vernier, and it's called graphical analysis. Or you could do Excel, but if you do Excel, you have to actually type in all the formulas and stuff like that. I would probably not do it that way. It's probably better to kind of use this graphical one. You could download this for free. Let me see here. Hang on here. So this is where you could kind of download it. I'm going to put the link here in the chat in just a second. But again, you could download it and it's free. And this is really what the instructions are written for in the experiment. So it walks you through how to use it and stuff like that. And again, I would recommend using this because it will be much easier than if you tried to sort of do it yourself and want to do that. So let me put that in before I forget. So this, I think, should get you to the software that you need to download it. And again, you're going to use that for really the data analysis in part 2 and also part 3 of the experiment. And it's going to help you make sort of that first derivative graph. It will also help you determine things like the pH, the pKa values, and all those type of things. Any questions on that there? Okay. Then that really kind of brings us to sort of part 3 of the experiment, which is, very similar to really part 2. The only difference is in part 3 of the experiment, we're going to be doing a titration with an unknown. So here, you're going to have an unknown solid acid in part 3, and you're going to try to determine the identity. You're pretty much going to do kind of the same situation here. Let's just pop that back up, I think. And let's go here. There it is. So in part 3 of the experiment, you're going to have an unknown acid, and it's going to be a solid. So you're going to weigh out a certain amount of it, grams of it. And you can kind of set it up the same way. You're going to dissolve it. You're going to put your acid basically in the flask. You're going to have your sodium hydroxide up here. And you're going to basically do a titration curve just like you did in part 2. So the goal here, again, is to get that whole titration curve all the way up to like a pH of 12, I think, again, is a place where you can stop. And once you do that, you're going to use the analysis tool as well to do some of the similar type of analysis. So you could figure out basically, again, the volume at the equivalence point. You could also figure out half the volume, the pH, the pKa value. And what you're going to do is then also figure out the molar mass. So to figure out the molar mass of your unknown acid, remember molar mass is grams per mole. So if we just think about the units, the grams part's pretty simple. It is pretty much what you weighed out. So that's the top part. The bottom part, which is the moles part, should come from your titration information. So from your titration information, you should be able to figure out, again, the volume of sodium hydroxide that you used. You will also, again, you'll have the volume of sodium hydroxide. You'll have the molarity of your sodium hydroxide. Again, using both of those things should get you to moles of sodium hydroxide. You then can use the mole to mole relationship from your balanced equation to go from moles of sodium hydroxide again to moles of your acid in this case. And that number is the bottom part that we would want to put in there. You could divide the two and it will give you the molar mass of it. Again, the molar mass is sort of a large number, 80, 90, 100, 200, 300, depending on what your unknown acid is. So it should be a relatively larger number in grams per mole. So that is sort of part 3. We're looking to identify what your unknown acid is. There should be a list of it as to possible unknown acids of what they are. And you'll be able to try to determine it using basically 2 pieces of information. You could use the molar mass that you calculated, and you'll also use the pKa value that you calculated. So just in case